Mapping multivariate data to color is a difficult problem. We present a tool called ColorMapND, which can accomplish this task. Its interface has four main parts. The color legend panel on the left assigns different colors to the data attributes or channels using a disc-shaped, perceptually uniform color space. In this panel, the vertical slider bar on the right allows users to rotate the color assignments and change the colorization of the image. The ring spacing slider allows users to choose the order and spacing in which the data attributes are coded into colors. The color contrast performs the color enhancement or compression of the colorized image by color-driven or data-driven modes. The bar charts on the bottom show the true values of a point chosen by hovering over it with the mouse. The main interface is the pseudo-colored plot. It displays the domain image that is colorized based on the chosen parameter settings and color assignments. The local enhancement panel allows users to select a local area by drawing a rectangle or polygon onto the colorized image. A color-enhanced version of that area then appears in the local enhancement window on the right. The visualization uses an extension of the disc-shaped color space. The channel view on the bottom displays the attribute or channel images one by one. Each channel image is colored according to the color assigned to its corresponding attribute in the color legend. This decomposition allows the user to focus on one attribute at a time. Our tool is fully interactive, and all displays are linked together. When the mouse hovers over a certain point in either the colorized image or the color map, it will display this point's channel values in the bar chart of the color legend panel. It will also mark this point in the individual channel images. This can help users in recognizing the fusion of the colors. Users are allowed to freely choose the colors that are assigned to the different attributes. They can create a personalized colorization to accommodate any preferences they may have. They can achieve this by rotating the attribute ring to the desired color configuration. A user can also enhance or compress the colorization that is shown. This color contrast enhancement supports a hue-preserving and data-driven mode. In both cases, the system first finds an elliptical region that captures the bulk of the data points on the color map. This elliptical region then serves as a lens. Users can expand the lens magnification to enhance the contrast of the main population of the data points. Or they can reduce the lens magnification to make the outliers more apparent. It is also often desirable to visualize the magnitude or strength of the data points. We accomplish this by mapping data point strength to opacity. In this way, more prominent points have a visually stronger appearance. The degree of emphasis can be controlled by a slider. The local enhancement panel allows users to select a local area by drawing a rectangle or polygon on the colorized image. A color-enhanced version of that area then appears in the local enhancement window on the right. This visualization uses an extension of the disc-shaped color space. It can therefore bring out details that could not be seen in the main colorized image. We now present a few applications. In the first example, we visualize a 4-material fluorescence dataset of battery material acquired with high-energy X-ray. Using ColorMapND, the scientists quickly identified the crescent area marked with a small circle. This area is mostly composed of gadolinium since its color is purple. Next, they focused on the small uniform area delineated with the white box. Using the local enhancement utility, they found that this area was in fact a composite structure of irregularly shaped zones of cobalt and iron. Color map ND can also colorize multivariate choropleth maps. We use the America's Mood Map dataset as an example. This dataset has 5 attributes that characterize each state by the personality and temperament of its population. The visualization on the bottom fuses these 5 attributes into a single color for each state. This combined choropleth map makes it easy to spot which states have similar and dissimilar personality profiles. At the same time, outlier states are also quickly identified along with their dominant personality trait. Multispectral images are another application we have tried. In this example, we fuse the RGB and UV channels of a flower dataset. We observe that the fused image has incorporated most of the detail of these partial images. The local enhancement of the white box on top of the colorization exposes an interesting UVC irregularity in the top petal. Finally, we colorized a multispectral terrain image comprised of 3 natural channels and 3 thermal channels. We find that the ocean part has a higher temperature than the mountain part since its color is more red. In the local enhancement image, we can observe a few remarkable hot spots in the mountain area.